Okay, get ready for this. What if you could literally control light at its most fundamental level? I mean, what if you could program the very atoms of a material to interact with light in ways that, until now, have pretty much just been science fiction? Well, it might sound like something out of a movie, but it is happening right now.
Think about it. What if we could build a sensor so incredibly sensitive it could sniff out a single dangerous molecule in the air? Or, on the flip side, create a display with colors so pure, so vibrant, that they would never, ever fade. Now, these two ideas might seem like they're from totally different worlds, but they're actually connected by the very same amazing breakthrough. And I want to be super clear. This is not some theoretical concept for the distant future. No, researchers are doing this as we speak. And the secret behind it all is this really fascinating and powerful class of programmable materials.
So, what is this secret ingredient? Well, it all comes down to something called phase change materials, or PCMs for short. And this is the engine that's driving both of the incredible revolutions that we're about to explore. So what exactly is a phase change material? Well, put simply, it's a substance that you can zap with a bit of energy, like a super fast pulse of light, and make it flip between two completely different physical states. The rockstar material here is called antimony trisulfide, and every single time it flips, the way it interacts with light changes just dramatically.
The whole mechanism is just brilliantly simple. You start with its first state, called the amorphous state, where all the atoms are just jumbled up, totally disorganized. Then you hit it with a quick pulse of energy, and that energy makes the atoms snap into a perfectly ordered crystalline structure. It's literally like flipping a switch at the atomic level. And that one simple change, that little atomic rearrangement, changes absolutely everything. In that messy, disordered, amorphous state, the material bends light one way. But once it's in that neat, ordered crystalline state, it bends light in a completely different way. This change in what we call the refractive index is the key. By switching back and forth between these two states, we get active, programmable control over light itself.
Okay, so we can control light. How do we actually use that power? Well, let's start with our first deep dive, building sensors that can detect things that are, for all intents and purposes, invisible. Let's think about a real-world problem, like hydrogen gas. It's a fantastic source of clean energy, right? But it's also incredibly flammable. A tiny, undetected leak could be absolutely catastrophic. So what we need are sensors that can scream danger when even just a few molecules are floating around. To pull this off, scientists are using this really wild optical effect called a phase singularity. Here's an analogy. Imagine a spinning top balanced so perfectly that the slightest puff of air makes it wobble like crazy. A phase singularity is the optical version of that. It's this point of perfect cancellation where light reflection just drops to zero, and the light's phase, it just shifts massively. And that point is incredibly sensitive to any tiny change in its environment. Now, here's the big breakthrough. The old methods, they could only create one of these super-sensitive points, and you had to hit it at a really steep, impractical angle. But by using this cleverly designed optical trap called a TAM cavity, built with our phase change material, researchers did something that was just incredible. They created two phase singularities at the same time, a dual phase singularity, at a single, low, and much more practical angle. And the result? Well, having two of these hypersensitive points doesn't just double your sensitivity, it amplifies it like crazy. This new design is 5 times more sensitive than the previous best-in-class technology. And when you actually look at the numbers, the difference is just, wow. The old method needed a steep 50-degree angle to get just one singularity. The new method works at a much easier 20 degrees and gives you 2. But the real bottom line is the sensitivity. It jumps from around 6,000 to over 33,000. That is a massive leap forward in our ability to detect the unseen. So that's how these materials are helping us see the invisible. But what about that other promise I made, painting with perfect, permanent color? To really get that, we need a quick little lesson in how color actually works. See, most of the colors we see in everyday life, like in paints or clothes, come from pigments. They work by absorbing certain wavelengths of light. The big problem, though, is that these chemical pigments break down over time, especially with sunlight. They fade. But structural color, that's different. It's created by physical nanostructures that reflect or scatter light, like a butterfly's wing. Its color comes from its actual structure, so it never, ever fades. The big challenge has always been that our man-made structural colors, well, they often aren't very pure.
You get these unwanted reflections of other colors creeping in, which makes the color you actually want look kind of washed out or milky.
The solution to this is another brilliant piece of engineering, the aperiodic Bragg reflector. Just think of it as a stack of ultra-thin mirrors made from our hero material, SR2S3, and silicon dioxide. Now, the real secret is in that word aperiodic. A normal reflector would have perfectly repeating layers, but here, the thickness of each layer is strategically varied, almost like a custom-tuned musical instrument. This design is engineered to cancel out all of those unwanted reflections, leaving you with just a razor-sharp band of pure, vibrant color.
And the results are absolutely stunning. This new method achieved a color purity of 88% for orange. Now, to put that in perspective, older technologies based on these materials were hovering around just 35 or 40% purity. This is a total game changer for creating vivid, high-definition displays.
But hold on, here's where it gets really mind-blowing. Because this perfect color filter is built with a phase change material, it's not static. The color itself is programmable.
So in its initial amorphous state, with all those disordered atoms, the structure is engineered to reflect a pure, vibrant orange.
And then boom, with a quick pulse from a laser, those sp2s3 layers flip to their crystalline state. The atoms reorder themselves, the optical properties change, and that exact same structure now reflects a brilliant red. It's dynamic, rewritable color.
So, we've got hypersensitive sensors on one hand and pure programmable color on the other. Let's just zoom out for a second and look at the bigger picture this is painting for the future of light.
You see, it all comes back to this one amazing material, antimony trisulfide. It's the common thread powering two completely separate revolutions. For sensing, its atomic flip lets us create dual-phase singularities, giving us detectors with incredible sensitivity. For displays, that exact same flip allows a custom-built reflector to tune its color output, creating colors that are pure, permanent, and programmable. At the end of the day, both of these breakthroughs are about the same thing, achieving a whole new level of precise, active control over light.
And that leaves us with a really fascinating question. We're moving from just passively observing light to actively programming how matter interacts with it. So now that we have this key, what other doors are we about to unlock? What will we design next?